All right, welcome to a breakdown. We're going to be breaking down the Chem and Physical Foundations of Biological Systems, the CP section. We're breaking down a section bank passage. Okay, this passage is from the section bank, and the section bank passages are known to be hard. They're known to be hard. So I'm going to show you guys exactly how to read this, how to make it make sense. Okay, because sometimes the passages can be a little, can be a little wet or tricky here and there. Okay, but this can be a little tricky, just a little bit. It's not too bad. Okay, it's not too bad. But the questions here are easy. The questions here are easy. All right. The passage, reading it can be a little tricky here and there. I'm not gonna lie, but the questions are relatively easy. So I'm gonna show you guys how to read this, how to make it make sense, almost like 99% of the time. I'm gonna show you guys how to highlight. Okay, when to highlight, how to highlight, because highlighting is very useful. Okay, they give you the tools to highlight, so use it. How to eliminate answer choices, so you pick the best answer. And yeah, how to save time while doing it, getting the best score possible. I got a 131, so I believe I could put my 2 cents here. I would have got 132 if I remember my kinematics equations, but whatever. We're not all perfect. So this is question number 1. I'm gonna go through these questions, guys. I want you to read the passage. Okay, read the passage by yourselves and pick your answer choices. Write them all down, and then go back to the video. Press pause. Press play. My bad. Press play. And then, hopefully you got everything right, or you see where you went wrong. Okay, so this is question number 1. Write down your answer choice. This is question number 2. Again, read, write down your answer choice. This is question 3. So next question. So next question. And this is the next question. It's the last question. Yeah, it's the last question. So pause it whenever you need to. Write down your answers, and hopefully we get everything right. And if not, you're going to see where you fucked up. All right, let's begin. Photoacoustic calorimetry is a technique used to determine the bond association enthalpy of solute molecules. All right, I've never seen PAC before. I have no idea what the heck PAC is. I don't even know why they even brought it up, but I'm highlighting this part here because it literally just tells me what the heck is going on. Okay, if I understand this, then all this will probably be a little more easier. Okay, so what is it measuring? What are we here to measure? What is the goal? Okay, what is the goal of this whole thing here? It is to determine the bond association enthalpy of solute molecules. You should know what bond association enthalpy is. Okay, it's the energy needed to break a bond, or the reverse, make a bond. Okay. PAC is based on the photoacoustic effect. I have no idea what that is, but they're going to tell us. In which matter emits sounds after it has absorbed light. A photoacoustic calorimeter schematic is shown in figure 1. Okay, this is the schematic, this is the figure. Okay, we're presenting a figure here. So when you're presented a figure, like a diagram like this in the CP section, okay, you don't want to spend too much time on it. You don't want to spend too much time, reading through it and trying to make sure you know everything. Briefly, like quickly look at it, okay, just so you know what the heck is going on. So what I would do is I would say, okay, pulse laser here. We have 12 centimeters here. We have a lens. Okay, you gotta know your lenses. You have a laser. The lens brings these laser rays together. So it hits a sample, and there's an energy meter, or as a microphone, oscilloscope. Okay, I got a good picture in my head here. So now we're just gonna keep reading. Again, you don't have to have a perfect picture in your head. You don't have to have a perfect understanding of it, but just keep reading. The monochromatic pulse laser beam is focused on the sample cell using a thin lens. Each photon causes the cleavage of a chemical bond in the solute molecules. Because the photon energy is designed to be larger than the energy needed to break the bond, the excess energy is absorbed by the solution, causing a local temperature increase. Okay, this is important here. The excess energy is absorbed by the solution, causing a local temperature increase. So right here, what the heck happened here? Okay, we broke the bond with the photon. We released energy. And because that energy is released, we get a local temperature increase. Okay, this fast and localized heating process, okay, this is already like ringing a bell to me here to highlight. Why? Because it just came out at me. Okay, whenever something comes out at you, like when you're reading, and something just sticks out, pops out in your head, or while you're reading it, you highlight it right away. Because usually the question will ask something about this pop out here. Okay, whenever something pops out in your head, or when something is like talking, like they're saying something about one thing, and then they'll say, oh, however, this happens. or they'll say blah, 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 but this happens. You know, whenever there's like a switch, then that's something to pay attention to. But here this pops out of my head, okay? It doesn't matter if you highlight the same things I highlight, okay? Just highlight whatever pops in your head, okay? You're going to encounter different passages, okay? I'm not going to tell you highlight this, highlight that. When you reach this, highlight this, okay? Just highlight whenever stuff pops in your head. It'll help you also to, you know, stay focused in the passages because it's pretty long. It's pretty freaking long. Okay? An hour and a half of straight focus, it's pretty long. This fast and localized heating process creates a sound wave that reaches the microphone, which sends the sound to an oscilloscope for recording. The amplitude of the sound signal is proportional to the amount of heat produced. Okay, I like this. Amplitude proportional to amount of heat produced. Okay, and that's delta H and R. The energy meter, based on the photoelectric effect, uses a detector with the work function of 3.4 electric volts. Okay, you have to know the photoelectric effect. You have to know it. Okay, what is work function? You have to know what that is. Okay, in the photoelectric effect, quick little, review here. You have photons hitting a sample or metal or whatever. The photons hit, and electrons are ejected. Okay, the photon comes with the energy. Electrons come out with the energy. It is not the same energy. Energy is lost going from a photon to an electron. Okay, how much of that energy is lost? 3.4. The energy in the photochemical reaction, delta HU, is the difference between the laser pulse energy, EM, and the heat detected, delta HNR. Okay, so heat detected minus the energy of the laser gives you, delta HU, which is the energy in the reaction. It makes sense. It makes sense here. It's not too bad. The bond enthalpy is determined as a ratio between delta HU and the efficiency of the photochemical process. It makes sense. Table 1 summarizes the values of the bond dissociation enthalpy of OH bonds in phenols, SH bonds in thiophenols, and CH bonds in alkyl benzenes, and the corresponding types of lasers used. And they give us a table here. When they give you a table with straight information, you never look at it. Okay? You look at it only when the question asks, you go ahead and you look at the table. Okay, don't try to look at the table numbers now, try to get a little, information in your head, try to help you. No. Only when the question asks, then you look at the table, okay? And it'll say in the question, oh, based on the table, this, okay? So only when they ask. If not, you're going to spend time in it and you're going to lose time, okay? You don't have much time. Based on the passage, an experimental feature that distinguishes the PAC technique from the classic calorimetry technique based on thermometers is that PAC can be used on samples with specific heats larger than water. Okay. The classic technique can. Okay. It could. So that one we could easily eliminate. Enables the measurement of fast and localized heat transfer processes. Okay, this sounds like a good answer. Let's see if there's a better answer. Is based on the second law of thermodynamics? No, that is no. Okay, that's one you could just chop out. Remember, if you have if you're looking at an answer choice, okay, and you're like, okay, this doesn't sound right, you chop it out right away. I don't care. You don't keep reading it. You're gonna read it and then you're gonna be like, oh my god, this might be right, and then you'll mess up. So just chop it out. Boom. It's useful on samples in the solid phase only. I don't remember much about calorimetry. I remember they used it for liquids. I remember in calorimetry, it would literally be like, they would have a chamber, and then a reaction would happen in the chamber, and the energy would be released, and then it would warm up some water. It will heat water, and then the change in temperature of the water is equal to the change in energy of the bond. Okay, so it's either B or D. Well, enables the measurement of fast and localized heat transfer processes. Well, we highlighted fast and localized heating process. Okay, in a regular classic technique, the regular classic calorimetry technique, the heat, the heat that's released, that warms up the water, which is actually the change in energy, which is actually the energy of the bond breaking, that is not localized. Okay, that just heats the water in a regular classic calorimetry technique. Okay, it just heats the water and we get the information and that's it. We move on. But this one, Okay, it's fast and localized heating process. It literally says it right in the passage here. Okay, it's proven right in this passage. It literally says it right in this passage. Also, like I said, I highlighted this because it stuck out to me. Okay, a lot of the times when you get good, and this is after like some, not even that many passages you got to do. Okay, when you get good and you keep reading, you keep doing it, you're gonna highlight stuff that sticks out to you. Okay, look, it's pretty obvious. They just threw it in there. They just threw it in there. This fast and localized heating process. Okay, so if it's like that word from word, then you're better off choosing that answer choice. So I'm gonna go with B here. I don't even think this is even right. I think I can eliminate this. I'm gonna go with B here. So let's see. Boom! There we go. All right, we got it right. And there's an explanation if you guys want to read. You could read it, pause it, whatever. Let's move on to the next question. What is the reading of the energy meter in Figure 1 when an appropriate laser is used in pack to dissociate a particular chemical bond? Energy meter. Okay. What is the reading when an appropriate laser is used in pack to dissociate a particular chemical bond? EM. No, that's the laser pulse energy. Okay. Remember, that's just laser pulse energy. So that's not even it. Okay, this is not it. Delta HU, no, that's the difference, right? Yeah, that's the difference. Okay. That goes to the water. That goes to not the water, no, it goes to the solution, which causes the temperature increase. That measures it. The whole entire microphone oscilloscope measures the dissociation energy. That's literally what the whole thing is about. Delta HU measures that. It goes over here. It doesn't go to the energy meter. That's not this one. Delta HNR. No, that's the heat detected. Okay, the heat detected is from the solution and the sound waves. It's proportional. See the amplitude. Okay, the amplitude of the sound signal is proportional to the amount of heat produced. Delta HNR. So it's not this one. So the process of elimination, I'm choosing D. But another reason why I think it would be D is because, well, when you think about it, it told us that the excess energy, okay, the excess energy is absorbed by a solution, causing a local temperature increase. So we need excess energy to make that increase. Also, it uses the word appropriate here. Okay, what is the reading of the energy meter in Figure 1 when appropriate laser is used? Okay, that gives me like a definition, like, hey, appropriate. We're not going to be using some crazy laser. We're going to use a right one, and that one is going to have the right amount of energy to break the bond. And that's it. We're not going to use a crazy, like, huge laser with a lot of energy in it. That will cause a lot of excess, and that will eventually could hit the energy meter. Appropriate. That's it. Nothing more. Okay. Answer is D. And there's the explanation if you guys want to read. Look how I answer these choices, guys. I'm very confident in the way I answer these answer choices, all right? That's how you have to be. You have to be confident when you answer these answer choices. If not, you're going to overthink and then convince yourself that a wrong answer is right. They throw distractor answer choices there for that reason, okay? They throw little distractor answer choices that sound right but aren't right. So you got to be careful of those, okay? Which structure is common to all three compounds mentioned in the passages that were studied using PAC? They were all phenols, right? This is phenol, thiophenol, alkylbenzene. Oh, this is benzene. They're all aromatic rings. All this aromatic. Okay, not alkyl, not carboxylic acid, not carbonyl. It's pretty easy. Okay. According to the passage in the data in Table 1, what feature must distinguish laser type A? Okay, again, look, according to the passage and data in Table 1. So you go straight to Table 1. You look at Table 1. They said, look at Table 1. Yeah, hold on, I can't talk. They said, according to the passage in the data in Table 1, okay, they said Table 1, so you go to Table 1. That's it. You go to Table 1. Which feature must distinguish laser type A, okay, from laser type C in order to be suitable for the cleavage of the bond specified? Laser type A must be better focused. Laser type C, okay. Well, we look at it, okay. We see we have 463 kilojoules per mole to break this, and this one we only need 349. So if we have more energy, that means we need more energy to break the bond, okay? We have less energy to break the bond. This is more energy to break the bond. If we have more energy to break the bond, if we need more energy to break the bond, we need a stronger laser. So laser type A must be stronger than laser type C. Be better focused, laser type C. Okay. Have a higher frequency than laser type C. Yes. Okay. Higher frequency means more energy. More energy means more potential to break the bond. This bond requires more energy, so we're going to need more energy. And higher frequency gives us more energy. Have a longer wavelength than laser type C. Okay, these two answer choices, you should see in your head that they're trying to test your knowledge of wavelength, of frequencies, of that proportion, of that fraction, of that equation. All right here, they're trying to test you with. Okay, this is a wrong answer choice. You should know from your content review that a longer wavelength does not mean more energy. A long wavelength means less energy. Okay, a higher frequency means more energy. So this you can get rid of. And because, okay, this is not all the time, but because they throw opposites here, they threw opposites here, okay? Usually this one's going to be right if they throw in an opposite here. They want you to make a decision. The MCAT wants you to make decisions. So you make the decision to go with the right answer choice. They have opposites here, okay? If they have opposites, usually the correctly opposite one is right. I would have all the answer choices. Emit fewer photons per unit time than laser type C. No, if laser type A emitted less photons per unit time, it would be weaker. We need laser A to be stronger. So this is wrong. Be better focused, laser type C. Again, this sounds right, okay? This may be right. This is for a fact right, but this may be right, okay? This is a okay answer. This is a good answer. So you choose the better answer. Remember, the better answer, okay, is usually the one that's more specific. Okay, but if it's going to be more specific, you need to have good evidence backing it up. Okay, so this has to be the right answer. This is not a good answer. This is a very good answer. So the answer I'm going to choose is B. Let's see if it's right. Let's go. Let's go. Let's go. Okay. Next question. Based on the ray diagram and the distance shown in figure 1, the focal length of the lens is what? Okay. You should know this is simple. Pseudo discrete here. So here's a lens. Okay. Here's a laser, and then they converge here. The light rays all come together here. Where the rays come together is the image. So this is the distance from image to lens. So this must be distance from lens to object. This is the object, this is the lens. So what we're going to do is we're going to use the equation. You should know this. 1 over F equals 1 over O plus 1 over I, or 1 over F equals 1 over DO plus 1 over DI, whatever you guys want. And your 1 over DO should be, I'm writing it down right now, it should be 1 over 12. Your 1 over DI, 1 over the distance from the image to here is 4. So it would be 1 over F equals 1 over 12 plus 1 over 4. And if you solve, okay, I'm solving right here real quick with my pen. So be here 1 over 3 equals 1 over F 3 centimeters. Okay, you could comment down below if you want a picture of the work I did, but you should get 3 here. What is the kinetic energy of a photon electron produced in the energy meter of the packed device when the frequency of an incident photon that is not absorbed in the solution is F equals 5 this and H equals this? They literally, okay, here's a cheat sheet, guys. Literally, they give you this, okay? They literally give you this. If they give you this, use the equation that has it. Don't think you could use another equation. Don't think they're going to use this to trick you, okay? They literally give you it, okay? How messed up is that if they gave you this and you need to use an equation that didn't have this, okay? They gave you this, so use the equation that has it. The energy of the photon electron, okay? That means after the photon hits the sample, we emit an electron. The photoelectron is the one that's emitted. What is the kinetic energy of that? Okay, in order to know that, we need to know the incident photon energy. And the incident photon energy is E equals H times F, okay? The energy of the incident photon is the H, which is not Planck's constant. This is H here times F. Okay, that's going to give us the energy of the incident photon. And when you do 5 times 10 to the 15 times 4.1 times 10 to the negative 15, okay, you're going to get 20.5 times 10 to the negative 10. Okay. Now, they want to know the energy of the photon electron produced. Okay, so photon hits, photoelectron produced. We lose some energy there. You have to know the photoelectric effect. Again, we lose some energy there going from photon to photoelectron. That energy lost is the work function. That's what it's called, the work function of 3.4 eV. So because we lost that energy, we're going to subtract, okay, 20.5 times 10 to the negative 10. Actually, no, not times 10 to the negative 10. This is 15 and 15. So forget the negative 10, okay? My bad, my mistake. It's going to be 20.5. That's it. So 20.5, okay, minus 3.4. Okay, we lost energy to go from photon to photoelectron. And if we lost that energy, we're going to subtract 20.5 minus 3.4. We're going to get 17.1. Okay. Yeah, I'm pretty sure that's it. Just disregard when I said 2 to the 10 to the negative 10. Okay, just disregard that. Should be right. And we got it right. And that's it for this one. Okay, guys. So, hope you guys enjoyed it. My bad for making that mistake here. Right here. Okay, just ignore that. All right, I told you I haven't seen this passage in I don't know how long. Okay, I don't remember this passage at all. This is me attempting it right away, first try. You know, never seen this before. So, we got everything right. Thank God. That's awesome. So, yeah, let me know what you guys think. Comment down below if you want more. Subscribe because we're trying to hit 1,000 within the next month, and that would be amazing. And yeah, just comment down below if you want more. So I'll see you guys in the next video. Peace.